Here we are going to learn how to design parity generator circuit and parity checker circuit. When we send our data due to any noise or any other issue, our data may change or may get corrupted. And in order to detect this type of error, we are using parity code. In our previous video, we have seen that how to detect error using parity code. But in order to send parity bit with our data, we must generate parity bit for our data. So in order to generate parity bit for our data, parity generator is used. Basically, parity generator are of two types: odd parity generator and even parity generator. Odd parity generator will be further classified into multiple types like multiple bit odd parity generator. We can say 2-bit odd parity generator, 4-bit, 6-bit, 8-bit, like that. And the same way it is true for even parity generator. So it's like you can have 3-bit odd parity generator, 8-bit odd parity generator, it's like 5-bit even parity generator, 8-bit even parity generator, like that. So now we'll understand entire process of designing parity generator circuit. And from this, first we are going to start with odd parity generator. So here is our 3-bit data with total 8 possible combinations with 3 bits. Now the question is, what should be the parity bit for all this data for odd parity? If you remember the definition of odd parity from our previous video, then pause this video now, then write the parity bit for entire table and then post it in comments. And if you have not seen the previous video, watch it later to clear your concept about parity code. So now we'll move further. So tell me, what is the definition of odd parity? So the definition is total ones in data including parity bit should be odd number. So as per the definition, the parity bit for all these 8 possible combinations are like this. So you can see in all 8 possible combinations, total count of ones including data and parity bit will be odd number. Let's take example of this number. So 1, 2 and 3. 3 is odd number. So total count of ones is in odd number. Let's take example of this. Over here also total count of ones is 1. So this is the odd parity for this data set. Now this is the boolean equation for odd parity generator. It is B2 bar, B1 bar, B0 bar, B2 bar, B1, B0, B2, B1 bar, B0, B2, B1, B0 bar. So this is the boolean equation for odd parity. But the question is how this was derived. There are 4 combinations where we want 1 as our parity bit and the rest are 0. So here when B0, B1 and B2 all these data bits are 0, how we can get 1 as parity bit? For that, here is the logic: B2 bar dot B1 bar dot B0 bar. When B0 is 0, B0 bar will be 1. When B1 is 0, B1 bar will be 1. When B2 is 0, B2 bar will be 1. So 1 dot 1 dot 1 gives us 1. The same way we'll go for this B2 bar dot B1 dot B0. You can see a tiny little bar symbol over here. Using this symbol, you can identify that it is normal B2 or B2 bar. So what we used to do in our data set where there is 0, for that bit we'll use bar and for rest of the bit we'll use B1 and B0 as it is, and the final result will be 1. So as per this logic, what should be the next combination over here? It's B2 dot B1 bar dot B0 gives us 1 in output, and finally B2 B1 B0 bar gives us 1. So now we'll combine them in order to get the final result. So that is how we get boolean expression for odd parity generator. Now we'll simplify this equation in order to generate logical circuit from this boolean equation. So from first 2 terms you can see that B2 bar is common. So we can take this common out. So we can rewrite as B2 bar dot into bracket B1 bar dot B0 bar plus B1 dot B0. like this. Now for next two terms we can see that B2 is common. So same way we'll write the next part. B2 is common and the remaining terms. Now here you can see that B1 bar into B0 plus B1 into B0 bar gives us B1 XOR B0. Same way B1 into B0 bar plus B1 B0 gives us B1 XOR B0 bar or B1 XNOR B0. So if we replace these two terms by these two terms, we can rewrite this equation as this. Now let's assume these term as A and this term as A bar. So now we'll replace this A over here and we'll replace this A bar over here. And we can rewrite this equation as B bar dot A bar plus B2 A. Now when you look this equation, it looks similar to this equation. So we can rewrite this equation as B2 XOR A bar or B2 XNOR A. It is actually B2, not B1, right? So B2 XOR A. Now let's see what is A. This is A, B1 XOR B0. So now we'll replace that A over here. So we'll rewrite this equation and it is like B2 XOR B1 XOR B0 bar. So finally this is the equation for 3-bit parity generator. Like this we can write equation for multi-bit parity generator. So here is the table for simplified boolean equation for parity generator for the data from 2-bit to 8-bit. The equation that we have derived is this one, which is for 3-bit. So simply what you're supposed to do, you're supposed to do XOR operation of all the bits and then do NOT operation of that. So that is how you can get simplified boolean equation or simplified boolean expression for odd parity generator. Now we'll jump to design a logical circuit from this equation. So this is a 3-bit parity generator equation that we have just developed. Now we'll create a logical circuit from this equation. First of all, we'll do XOR operation between B0 and B1. So in this circuit you can see this is the symbol of XOR gate. So we are doing XOR operation of B0 and B1. Then the output of these two will be utilized to do XOR operation with B2. So here you can see the output of these two, the output of XOR operation of these two is utilized to do XOR operation with B2. And the output of that will be given to the NOT gate in order to do the NOT operation of this boolean expression. And finally we'll get parity bit. So this is the logical circuit for 3-bit odd parity generator. But now it's time to verify that whether this circuit is true or not. We'll write truth table for this XOR gate and we'll write truth table for this NOT gate. Now let's take any of the data. Let's say we are going to deal with this data. So B2 is 0, B1 is 1 and B0 is 1. So we'll implement this over here. So B0 is 1, B1 is also 1. So over here when B0 and B1 both are 1, the output of this XOR gate is 0. So we'll get 0 over here. In this data B2 is already 0. So this B2 is 0. So when both the input to the XOR gate is 0, the output will be 0. So output will be 0 over here. When the input to NOT gate is 0, the output will be 1. So output we are getting here will be 1. So the parity bit will be 1. So check over here whether the parity bit is 1 or not. Now let's see another example. So here you can see B0 is 1, B1 is 0 and B2 is 0. So for this XOR gate, when one input is 1 and the another one is 0, the output will be 1. So here we'll get 1 as output. Now we'll talk about this. When one input is 1 and another one is 0, the output of this XOR gate will be 1. So we'll get 1 over here. And when the input to NOT gate is 1, the output will be 0. So we'll get 0 over here. So our parity bit will be 0 and the same 0 parity bit we are getting in our table. Hence it proves that this circuit is true and working properly. So this is odd parity generator. Now we will understand even parity generator. This is our data for even parity generator. Now what should be the parity bit of this data? If you remember the definition of even parity, then pause the video and write the parity bit for this entire table. and comment it in comment section. And if you are not clear about it, you can watch my previous video later. Now let's see the definition of even parity. The total ones in data including parity bit should be even number. So as per the definition, this is the table of parity bit for our data. You can check over here, the total numbers of 1 in any of the data set will be a even number. Now in order to get boolean equation for even parity, we'll form equation from this. This same logic we have used for odd parity, this we are going to use for even parity. b2 bar dot b1 bar dot b0 is equal to 1, which is this one as parity bit. The logic for all this possible combination is the same as odd parity. So now combining all this will gives us final equation for 3-bit even parity generator, which is this one. And here we are going to simplify the equation the same way as we did earlier. So this is the simplified equation for 3-bit even parity generator. You can pause the video, you can go through an entire simplification process. The process is more or less similar to the odd parity generator. If you have any doubt in this, you can ask your doubt in comment section. But because it is the same explanation, we are not going to repeat it in this video. And now we'll move further. Here you can see all the equations for even parity generator for different bits of data, from 2-bit to 8-bit data. And if the data is even larger, you can extend this expression further. So now this is the equation for 3-bit parity generator that we have developed, and using this equation now we are going to develop a logical circuit. Now what we'll do XOR operation of B0 and B1. Here it is, and result of this will be utilized to do XOR operation with B2 over here, and finally we'll get parity bit in output. Now let's just verify that the circuit is working properly or not. Let's take this example. We have data 0, 1, 1. So our B0 is 1, B1 is 1 and B2 is 0. When both the input to XOR gate is 1, the output will be 0. So we'll get 0 over here. Now both the input to this XOR gate is 0, and when both the inputs are 0, the output will be 0. So the parity bit will be 0, and the same 0 parity bit we can see over here. Now let's take another example. Let's say we'll take this example. So this is the data 1, 0, 0. So B0 is 0, B1 is 0 and B2 is 1. So when both the input to XOR gate is 0, the output will be 0. So we'll get 0 over here. When one input is 0 and the another one is 1. So one input is 0 and the another one is 1. The output is 1. So we'll get 1 over here. And the same one we are getting here in our parity bit table. Hence it proves that our circuit is correct and working properly. So this is how even parity generator circuit works. So till this section we have cleared the understanding of parity generator. Now it's time to understand what is parity checker. We have seen earlier that how to generate parity bit at generating side over here. But now it's time to understand parity checker at receiving side over here. That how we are going to check whether the data we have received has any error or not. So in this section we are going to explore parity checker. The same way as parity generator, parity checker has two types, odd parity checker and even parity checker, and they both are also available in multi-bit format, 2-bit, 3-bit or multi-bit parity checker. Now let's take an example of data set. Let's say this is our 4-bit data where 3 bits are of data bit and 1 bit is for parity bit. So at receiving end it will become a 4-bit data set or a 4-bit data. Now we'll understand how to design odd and even parity checker for this data set. So first of all we'll start with the odd parity checker. Here this is our data set, a 4-bit data set for odd parity checker, and now let's see what should be the output for the parity checker circuit for this data set. So as per the definition of odd parity, all ones in the data set including parity bit That means we are talking about entire data set. So all the data including parity bit should be odd number. So if we consider example of this data set, all the ones in this is even number, so which is false condition. So the parity checker circuit should be 1 in order to show some error. So this is how the parity checker bit should be for this data set. So whenever ones in odd number, the parity checker will be 0, and whenever the ones is in even number, the parity checker should be 1 in order to show error in the data. Now here you can see that this table is similar to that of odd parity generator for 4-bit data, and previously in the same video we have seen a simplified equation for 4-bit data. The equation looks like this for 4-bit data. So what we'll do now, we'll not derive the equation. The process is the same process as we have did earlier. So now here we'll directly use the equation. So the simplified boolean expression for parity checker circuit is like this: B2 XOR B1 XOR B0 XOR parity bit P, and then finally the NOT operation of all these things. So as per this equation, if we design logical circuit, then it looks like this. First we'll do XOR operation of B0 and P, so here it is. Then we'll do XOR operation of B1 and B2, so here it is. And then the result of these two will be utilized to do XOR operation, this one, so here it is. And then finally the result of all this XOR operation will do the NOT operation, which is at the end. So this is the logical circuit for this boolean expression. And now we'll verify that the circuit is true or not. These are the truth table for XOR gate and NOT gate. So let's pick any of the example. Let's say we are utilizing this example. So 0 1 1 0 is our data. So 0 1 1 0, this is our data. So XOR operation of 0 and 1 gives us 1. XOR operation of 1 and 0 gives us 1. Now XOR operation of 1 and 1 gives us 0. NOT operation of 0 gives us 1. So the parity bit should be 1. And in same example you can see that the parity checker bit is 1. Now let's take another example. Let's say this one. Our data is 1 0 1 1. So 1 0 1 1. So the output of XOR gate when the input are 1 and 0, the output is 1. And the output of XOR gate when both the inputs are 1, the output will be 0. So again, when one of the input of XOR gate is 1 and the another one is 0, the output will be 1. And when the input to NOT gate is 1, the output will be 0. So in same example, you can see that the parity checker circuit should give 0 in output. And that is what we are getting over here. That means that this circuit is perfect and correct circuit. So after this odd parity checker circuit, now we'll jump for the even parity checker circuit. This is our 4-bit data for even parity checker. What will be the definition for even parity checker? All the ones including data and parity bit should be in even number. So if you check for this example, all the ones over here are in even number. So the parity check circuit should give 0 over here, and here it is in odd number. So the parity check circuit should give 1 over here. So according to this, if we write the table for parity check circuit, here is the entire table. Now you can see that this data table is similar to that of even parity generator for 4-bit, and there we have seen the simplified equation for 4-bit data. The equation for 4-bit data looks like this. So what we'll do, we'll directly use this equation for even parity checker. So the equation for 4-bit even parity checker is B2 XOR B1 XOR B0 XOR P. So using this equation, if we develop a logical circuit for even parity checker for 4-bit, then the circuit looks like this. So first of all, we'll do the XOR operation of B0 and P. Here it is. Then the XOR operation of B1 and B2, here it is. And then the XOR operation of the result of these two, here it is. And finally we'll get parity checker output. So let's check whether the circuit is true or not. Let's take an example of this data set. All the inputs are 0. So when both the inputs to XOR gate is 0, the output is 0. So 0 over here and 0 over here. And again, when both the input to XOR gate is 0, the output is 0. So we'll get 0 over here. And the same way we are getting 0 over here. Now let's take one more example. Let's say this one 0 1 1 1. So 0 1 1 1. When both the input to XOR gate is different, the output is 1. And when both the input to XOR gate is same, the output is 0. Again, we'll use the same logic. When both the input to XOR gate is different, the output is 1. So the output of parity checker circuit will be 1 and we'll get 1 over here. So this one indicates that there is something wrong with the data we have received. So this is how even parity checker circuit will work. So in this video we have understood how to design parity generator circuit and how to design parity checker circuit. In next video we'll see other methods of error detection and correction. And to learn that, watch the next video into the playlist. See you into the next video.